Hello, viewers. In today's session, we are going to discuss another important and conceptual problem from the topic sphere, right? And here we are going to discuss the concept of plane section of a sphere using this important problem, right? So here we have to find the radius and center of the circle whose equation is given by the combined equation of a sphere and a plane, right? So let us first see the concept of plane section of a sphere, and then we'll solve this problem. So now consider a sphere whose center is say O, right? And O is the center of this sphere whose general equation can be written as x square plus y square plus z square plus 2ux plus 2vy plus 2wz plus d is equal to 0, right? And let us denote the sphere by the letter S. So S is the equation of this sphere having center O, right? And the coordinates of the center of the sphere are given by minus u, minus v, and minus w, right? And the radius of this sphere, say r, is given by square root of u square plus v square plus w square minus d, right? So now consider a plane whose Cartesian equation is given by Lx plus My plus Nz is equal to P, right? So now here we have a sphere that is S and a plane P, right? Now whenever a plane P it intersect a sphere S, then we always get a circle, right? Suppose this plane P cuts this sphere S, then the section of the sphere so obtained is known as a circle. And always remember that the combined equation of a circle is given by the equation of the sphere S and the plane P, right? So the circle is always represented by the equation of the sphere, that is S is equal to 0 and P is equal to 0. So the combined equation of the sphere and the plane gives us a circle. So now let us draw a rough diagram when a plane P intersect or cut a sphere S, right? And the section of the sphere is known as a circle, and let us draw the circle here. So we'll get a circle like this, right? So this is a circle which is obtained by the intersection of the plane P and the sphere S. And let us here denote the center of the circle by the letter C, and here we have a point, say A, right? And A is the point which lies on the sphere S. So the situation is that this plane P, this is the plane P, and this plane P cuts the section of a sphere S, which is a circle, right? And if we join this O and this point O and this point C, then OC is perpendicular to the plane of the circle, right? And let us draw this line, that is CA, and here let us join the point O and A. Now from this figure we can see that OC is perpendicular to the plane of the circle, or in other words we can say that OC is perpendicular to this plane P. And if we draw the normal to this plane P like this, then this normal vector n it is parallel to this line, that is OC. So now from this triangle, that is triangle OCA, we can see that OC is perpendicular to the plane. It implies that OC is parallel to the normal vector to this plane P, right? So here OC is parallel to the normal vector, and here angle OCA is 90 degrees. And remember, this point A, it lies on the sphere. So OA is the radius of the sphere, right? Radius of sphere. And OC is perpendicular to the plane of the circle, right? Okay, so now if we apply the Pythagoras theorem to this triangle, that is right angle triangle OCA, then we can easily write OC square plus CA square is equal to OA square, right? Now OC is the length of the perpendicular that is drawn from this point O to this plane P. So OC can be taken as the length of the perpendicular from the point O to the plane P, right? And we already know the formula to find out the length of the perpendicular from a given point to a given plane, right? So let us take OC as lambda. Lambda is the length of the perpendicular from this point O to the plane P. So here we can write lambda square, and CA is the radius of the circle, right? Radius of the circle. So here we can take CA as R1. So we have R1 square, and OA is the radius of the sphere, that is R. So here we have R square. So from this equation we can easily find out the that is the radius of the circle, that is R1 square is equal to R square minus lambda square. So R1 is equal to square root of R square minus lambda square. So now let us quickly summarize what we have discussed so far. So we have a sphere S and a plane P, right? And when this plane P cuts a section of the sphere S, then we get a circle whose center is C, and the radius is CA, right? And the equation of the circle is given by the combined equation of the sphere and the plane P. So this equation, that is x square plus y square plus z square minus 8x plus 4y plus 8z minus 45 is equal to 0, and x minus 2y plus 2z minus 3 is equal to 0, together represents this circle, that is whose center is C and the radius is CA. So now let us find out the radius and center of this circle using this concept, right? So let us compare the equation of the sphere with this general equation. So here we have 2u, so we can write 2u is equal to minus 8, then we have 2v, 2v is equal to 4, and then 2w is equal to 8, and here d is equal to minus 45. So from here we get u is equal to minus 4. From here we have v is equal to 2, and here we have w is equal to 4, right? And the center of the sphere O is given by minus u comma minus v comma minus w. So from here the center O is given by minus 4, then we have minus 2 and minus 4. So this is 4 comma minus 2 comma minus 4, right? So here we can write 4 minus 2 and minus 4, right? Okay, now let us obtain the radius of the sphere. So the radius of the sphere, that is OA square, is equal to r square, because we are taking r as the radius of the sphere, and this is equal to u square plus v square plus w square minus d. So we have r square as here u is minus 4, so minus 4 square, then we have 2 square, then we have 4 square, and minus 45. So this is 16, this is 4, this is 16, and this is 45. So this is 32 plus 4, that is 36 plus 45, so this is 81. So r is square root of 81, that is 9, right? So the radius of the sphere S is given by 9 units. So now let us find out the length of the perpendicular, that is from point O to the plane P. That is we have to find the value of lambda, and from the theory of a plane we know that lambda is given by the formula, that is Lx1, then we have my1 plus nz1 and minus p divided by square root of L square plus m square plus n square, right? So this is the formula for getting the distance of a point from a plane. So here we have the equation of the plane as Lx plus my plus nz minus p is equal to 0. So here we can take this point, that is O, as x1 y1 z1. So we'll substitute this point in the equation of the plane, and then we take the absolute value, and then we divide by the square root of the sum of the squares of the coefficients of x, y, and z, right? So here we have lambda is equal to here we'll write, see, the equation of the plane is given as x minus 2y plus 2z minus 3 is equal to 0. So if we compare this equation with this one, then the value of L is 1, and the value of m is given by minus 2, and the value of n is 2, and p is equal to here 3, right? Okay, so now we have to substitute this coordinate in this equation. So we have 1 times 4, then we have minus 2 times minus 2, then we have 2 times minus 4, and here we have minus 3, and then here we have 1 square plus minus 2 square and 2 square. So let us simplify it. So this is 4 plus 4, then here we have minus 8, then we have minus 3, and here we have square root of 9. So 1 plus 4 plus 4, and here we have 4 plus 4 is 8, 8 minus 8 is 0, so mod of minus 3, and here we have 3, and here we have 3 over 3, so mod of minus 3 is simply 3, and here we have 1. So the value of lambda is equal to 1 unit, right? So the length of the perpendicular from the center of the sphere O to the plane P, that is lambda, is equal to 1. So now using this result, we can find out the radius of the circle, that is CA. So CA is equal to R1, that is square root of R square minus lambda square. So R is given by 9. So 9 square minus 1 square, lambda is 1. So this is 81 minus 1. So this is square root of 80, and that is square root of 16 times 5. And from here we can take 4, and this is 4 root of 5, right? So the radius of the circle, that is CA, is given by 4 times square root of 5 units. So now we need to find out the center of the circle C. So now to get the center of the circle, that is C, we have to make use of the concept of the symmetrical form of the equation of a straight line, right? And we know that the equation of a straight line is given by x minus x1 over say y minus y1 over b, and z minus z1 over c, where x1 y1 z1 is the point lying on the line, that is the line is passing through some point, and a b c are the direction ratios of the line. So here we'll find out the equation of this line, that is OC, and OC is already perpendicular to this plane P and parallel to the normal vector, right? So here we have OC, and the point O is 4 minus 2 minus 4, right? And the direction ratios of OC are same as the direction ratios of the normal vector, because this line OC is parallel to the normal vector, and the direction ratios of the normal vector are given by the coefficients of x, y, and z. So here we have 1 minus 2 and 2, right? So now the equation of OC can be written with the help of this equation. X1 y1 z1 is 4 minus 2 minus 4, and A, B, C are the direction ratios of the normal vector to this plane P. And since parallel vectors have either direction ratios equal or proportional, so here the direction ratios of OC can also be taken as 1 minus 2 and 2. So A, B, C are 1 minus 2 and 2. So we can now write x minus 4 over 1. Then we have y minus minus 2 over minus 2, and z minus minus 4 over 2. So we can now write x minus 4 over 1 is equal to y plus 2 over minus 2, and z plus 4 over 2, right? So this is the equation of this line OC, right? So now let us make use of the concept of general point lying on a line. So now let us introduce a scalar, say a mu, and mu is some real number, and mu is not equal to 0. So the purpose of introducing this scalar mu is to get the general uh, that is the coordinates of the general point, right? So here we can now write x minus 4 over 1 is equal to mu. Then we have y plus 2 over minus 2 is equal to mu, and z plus 4 over 2 is equal to mu. So from these three equations, we can now write x is equal to mu plus 4, then y is equal to minus 2 mu minus 2, and z is equal to 2 mu minus 4, right? So now since the equation of this line OC is given by this equation, and these coordinates may represent this point C for some special or particular value of this scalar mu, right? So now we need to find out the value of mu so that we can get the coordinates of this point C. So now for some value of mu, the coordinates of the point C may be written as mu plus 4, then minus 2 mu minus 2, and 2 mu minus 4. Now here again we have to make use of an important concept, that is when this plane P, it makes a plane section on this sphere S, then this circle, that is the center of the circle C, it lies on this plane P, right? So it implies that the center C, it lies on the plane P, so that this coordinate, it satisfies the equation of the plane, right? So the center of the circle, it lies on this plane P, so this coordinate must satisfy the equation of the plane. So here taking x is equal to mu plus 4, then we have minus 2, y is minus 2 mu minus 2, and then we have 2 times z. Z is 2 mu minus 4, and that is minus 3 is equal to 0. So now let us solve this equation for mu. So we have mu plus 4, then we have plus 4 mu, then we have plus 4, and then we have 4 mu, and minus 8 minus 3 is equal to 0. So here 4 plus 4, 8, 8 plus 1, 9. So we have 9 mu. Here 4 plus 4, 8, and 8 and 8 get cancelled, so we are left with only minus 3, right? So from here 9 mu is equal to 3, so mu is 3 over 9, and the value of mu is now equal to 1 over 3, right? So now we can substitute the value of mu in this coordinate to get the coordinates of the center of the circle. So now we can write the coordinates of the point C as mu plus 4. Mu is 1 over 3. Here we have plus 4. Then we have minus 2 over 3 minus 2. Then we have 2 over 3 minus 4. So this is 1 plus 12 over 3. This is minus 2 minus 6 over 3. This is 2 minus 12 over 3. And this is 13 over 3. This is minus 8 over 3. And this is minus 10 over 3. Right? So viewers, the coordinates of the center of the circle, that is C, is given by 13 over 3 comma minus 8 over 3 comma minus 10 over 3. So viewers, this is how by the application of all these concepts, we can easily find out the radius and center of the circle, which is represented by the combined equation of the sphere and the plane, right? And it is important to note that whenever we get a circle by a plane section of a sphere, then the combined equation of the sphere and the plane is represented by that circle, right? And moreover, here it is important to note that the section of a sphere by a plane passing through the center of the sphere is called a great circle, right? So when this plane P, it passes through the center of the sphere, then the circle so obtained is known as a great circle, and its center and radius is same as that of the sphere, right? So when this plane passes through the center of the sphere, then the circle so obtained has the same radius and the same center as that of the sphere. Hello viewers, in today's session we are going to discuss another important concept from sphere. and here we are going to discuss the concept of tangent plane to a sphere at a given point, right? So here we'll discuss this concept with the help of this problem where we have to find the equation of the plane tangent to the sphere whose equation is given by this second degree equation: x square plus y square plus z square minus 2x minus 4y plus 2z minus 3 is equal to 0, and we have to find the equation of the tangent plane to this sphere at this point, that is minus 1 comma 4 comma minus 2, right? So let us start. So let us now consider a rough diagram of this problem, and here we have a sphere and whose center is say O, right? And let us draw a plane like this. This is a plane, and this plane is tangent to this sphere at this point, right? And let us call this point as point P, right? And this point P is known as the point of contact, right? So point of contact is the point where a sphere touches a plane, and here we are given the coordinates of the point of contact P as minus 1 comma 4 comma minus 2, right? And the equation of the sphere is given as this, right? Okay, so now we have to find out the equation of this plane P, which is tangent to this sphere at this point P, right? So now let us consider the general equation of a sphere as x square plus y square plus z square plus 2ux plus 2vy plus 2wz plus d is equal to 0, right? And let us consider the equation of this plane as say ax plus by plus cz is equal to say d1, right? And the center of this sphere is given by the coordinates, that is minus u minus v and minus w. So the coordinates of the center of the sphere is given by minus u comma minus v comma minus w. So now let us compare this equation with this one. So here we have 2ux, and here we have a minus 2x. So 2u is equal to minus 2, and here we have 2vy, here we have minus 4y. So 2v is equal to minus 4, and here we have 2wz, and here we have 2z. So 2w is equal to 2, right? So from here we have u is equal to minus 1, because minus 2 over 2 is minus 1. From here v is equal to minus 2, and w is equal to 1, so that minus u is equal to 1, and minus v is equal to 2, and minus w is equal to minus 1. So the center of this sphere is now given by the coordinates 1 comma 2 comma minus 1. So here we can write 1 comma 2 comma minus 1. So now the next step is to join the point O and the point P, right? So when we join this point O and this point P, then OP is perpendicular to the plane, right? Or the tangent plane. And here O is the center of the sphere and P is the point of contact, right? So now OP is perpendicular to this plane. So let us find out the direction ratios of OP, right? So to get the direction ratios of OP, let us consider the point O as x1, y1 and z1, and the point P as x2, y2 and z2. So the direction ratios of any vector joining two points may be obtained by subtracting the coordinates. So we have x2 minus x1, then we have y2 minus y1 and z2 minus z1. So now we can write the direction ratios of OP as minus 1, minus 1, and then we have y2 is 4, so we have 4 minus 2, and then we have z2 is equal to minus 2 minus minus 1. So we can now write here minus 2, this is 2, and this is minus 2 plus 1, that is minus 1. So the direction ratios of OP are minus 2, comma 2, comma minus 1. So now let us draw the normal vector to this plane P, right? So the normal vector of this plane P may be drawn like this. And from this figure, we know that this normal vector is perpendicular to this plane, and OP is also perpendicular, right? So OP is perpendicular to the plane. It implies that this normal vector n is parallel to this line, that is the radius, that is OP, right? So vector n is parallel to OP. So this implies that the direction ratios of the normal vector to this tangent plane are same as the direction ratios of OP, right? Because from vectors we know that if two vectors are parallel, then their direction ratios are either equal or proportional. So the direction ratios of vector n may be taken as minus 2, 2 and minus 1, right? So now we are in a position to find out the equation of this tangent plane, because we know a point P which lies on this plane, right? And it is important to note that this point P, it also lies on this sphere, right? Okay, so now the equation of any plane which passes through some point, say x1, y1, z1, and having direction ratios a, b and c, is given by a times x minus x1 plus b times y minus y1 plus c times z minus z1 is equal to 0, where a, b, c are given by minus 2, 2 and minus 1, right? So here we have now a minus 2, then we have x minus x1, x1, y1, z1 may be taken as this point P, which is minus 1, 4, comma minus 2. So here we have minus 1, then B is 2, and y minus 4, y1 is 4, and then c is minus 1, and z minus minus 2, and this is equal to 0. So now we can simplify this equation. So we have minus 2, this is x plus 1. Here we have 2y minus 8, and this is minus 1, and z plus 2 is equal to 0. So from here we can now write minus 2x, then we have minus 2 plus 2y minus 8, and then we have minus z minus 2 is equal to 0. So this is minus 2x plus 2y. Here we have minus z, and this is minus 2 minus 8 and minus 2. So this is minus 12, right? So now multiplying both sides by minus 1, we can also write this equation as 2x, and then we have minus 2y, and then we have here plus z, and plus 12 is equal to 0, right? So this is the required equation of the tangent plane to this sphere, where the point of contact P has the coordinates -1 comma 4 comma -2.